Hello. Right, so if this had been a mathematics course, we wouldn't have needed the next two lectures, because I have shown you that for linear nth order ordinary differential equations, solutions exist. They're unique. They're globally defined. What more do you need? Well, there is the pesky business of the problem sets, and none of them contain any proofs, which is, of course, disgraceful. But anyway, proofs is something that you do on your own, and you're in the privacy of your library table or in one of your confabs with your friends in mathematics. What I will do is I will try to show you how to solve some of the examples of the equations of the kind of equations that I described yesterday. So the simplest example, well, actually not the simplest, but a simple example, which largely encapsulates the kinds of equations that you are likely to end up solving soon, at least, is somewhat general. It's an equation that says y double prime plus some function of x times y prime plus some function of x times y equals to some function of x. And the Cauchy problem for it is to require that it's equal to that y is equal to something at y naught, and you need the second condition. Remember that what we're actually looking at, right, is a system of two first-order ordinary differential equations for two functions, one of which is y, and the other is y prime. Right? So I need two initial conditions, or boundary conditions, you can call them. One that tells you what y is at some point, and one that tells you what y prime is at that point. Right? So if you want, in other words, if you want to solve a second-order differential equation uniquely, you have to specify not just where the solution starts, but also at what rate. Okay? So, and this is, on an intuitive level, this is very easy to understand, because what does this equation really do? It tells you what y double prime is in terms of y prime and y. Right? So if you're going to know what, so this and this, you'll need to know initially. So I could rewrite this equation as a 2x2, as a two-dimensional system, and simply just apply to it precisely the formula that I derived last time. And this is done in my notes as an example. But I trust you that to be able to substitute things into things. And so I will do this in a slightly different way, and then it'll be an exercise for you to figure out the connection between this new way of doing things and what I did last time. So, and this is a great thing to do in the pre-Christmas period, because this is a kind of ordinary differential equation buy one get one free deal. Now, what do I mean by that? Remember that what the story was for how to construct a solution. The story was that you need two linearly independent solutions of the homogeneous part of the equation, right? And if you've got that, then it's clear what to do, right? Now, getting two linearly independent solutions of a general equation like this, or at least seeing that instantly, is usually quite hard. I might show you an example of how to do this in one particular case, but generally it's quite hard. But let's imagine for now that you can stare at it and guess one such solution. Right? Just guess a solution of the homogeneous equation. Okay? So the homogeneous equation means we temporarily set this to 0 and look at this equation and ask, right, let's imagine that y1 of x is a solution of the homogeneous equation, right? And how you obtain that is nobody's business, right? So then we do what I've already done twice and what I will do several times again. I will look for a general solution in the form which is the particular solution that I have found times a constant that's been upgraded to a function. Okay? So, this is just, again, look for solutions in this form. At this point, you know, it's an entirely legitimate step, and you know, if it works, great. If not, then this was a stupid idea. But you know, why you should do this is something that one can examine a posteriori. So let's see what this does. But if you want this to be respectable, don't call it a substitution. Call it an ansatz. Right, and then you're doing something serious. So y prime. Let's see. So what's y prime? Y prime is psi prime y1 plus psi y1 prime. Y double prime is the prime of that, which is psi double prime y1 plus psi prime y1 prime plus another one like that plus psi y1 double prime. So now let's substitute these two into the equation. So if I do that, so y double prime becomes psi double prime y1 plus 2 psi prime y1 prime plus psi y1 double prime. That's the first term. The second term is a times that. So psi prime y1 plus psi y1 prime. The third term is b times psi y1. And equals to f. It's the equation is inhomogeneous. So the only purpose for which I used the homogeneous equation was to guess the solution y1 of it, right? But I'm solving the inhomogeneous equation. Well, since y1 is a solution of the homogeneous equation, all these terms cancel. Because y1 double prime plus ay1 prime plus by1 is equal to 0. So, and the highly beneficial effect of this ansatz has been to lower the order of the equation, because what you now have is an equation, a first order equation for psi prime. Let me make this obvious by rewriting it in the following way. Psi double prime, that's the first term. So I can divide through by y1, right? So take this whole equation and divide it through by y1. So that becomes this plus 2 y1 prime over y1. That's the first part of the coefficient of psi prime. And the other one is a. So plus a times psi prime. And that's that. And that's equal to f over y1. Okay? So this is a linear. This is a linear equation, first order linear equation for psi prime. So first order linear equation for psi prime. Well, I have already taught you how to solve these equations completely generally. Right? So psi prime, I will just write down the solution, and you can look it up in your notes or mine. So psi prime is going to be the following. So there is that quantity E of x that I have defined. I will rewrite its definition in a moment. Constant plus integral from x naught to x dx prime, the right hand side, which is f of x prime over y1 of x prime, and divided by E of x prime, where E of x is the exponential of minus the time integral of the coefficient in front of this. Right? So x naught to x dx prime 2y1 prime of x prime over y1 of x prime plus a of x prime. So notice that the first part of this can be integrated because this is a full derivative, right? Y prime over y is a derivative of a log. Right? So this here is d by dx prime of log y1, of log y1. So I can integrate the whole thing, and that would give me y1 of x naught divided by y1 of x squared exponential minus integral from x naught to x dx prime a of x prime, like that. So this is psi prime, and well, we need the solution, right? So we need now to integrate this. And that we just do explicitly, right? So yx is equal to y1 of x times psi, which is the integral of that expression, which is another constant, plus c1 from x naught to x dx prime e of x prime, and plus x naught to x dx prime e of x prime from x naught to x prime dx double prime f of x double prime over y1 and over e of x double prime. That's it. I have found the solution explicitly with two constants at the ready to satisfy any initial condition you like. So plug this into the initial, ask for initial conditions to be satisfied in order to find the constants. So, and this is done for any right-hand side and any coefficients. Now, as an exercise, go back to the derivation of last lecture and try to map this solution onto the formula that I derived. Okay? So now this is not quite so. Even though this is quite impressive that we can take a general equation and do such a thing, our ability to do that depended on being able to guess at least one solution. Right? It didn't have to be general, but it had to be a solution. So now, the question then is are there any general strategies for doing that? Right? And the answer is general, no, but there are some strategies. Well, actually, generally, the strategy is to despair. Right? Because if I write down a random equation of that sort for you, you won't be able to guess a solution because most of most such equations do not have solutions in quadratures. Right? However, when you encounter an equation in a problem set, the additional essential piece of information is the selection effect. It's in the problem set. If it's in the problem set, it's overwhelmingly likely that it can be solved in quadratures. Unless, of course, the person who typed up the problem set committed a typo in that equation, in which case generally speaking, it won't be solvable. Okay? So anyway, the strategies, so generally speaking, you can't. In many particular cases, you can. There is actually I'll say one more thing. And one thing that you will encounter in your problem set for this week is kind of a recipe for what to do if you can't, right? And one of the things that you can do is you can try and derive the solution not in quadratures but as a series, right? So sometimes it's possible to derive a Taylor series that satisfies your equation. And if you can derive one, then according to this principle, you can derive a second one. Right? So that's about as general a strategy as exists. There are actually, so another general strategy which I mentioned before was to declare the solution known. Meaning that you have an equation, you don't have a solution to it, and you say the solution to this equation is called, my function, right? My new special function. And I'm now going to, in some way, study that solution to death and familiarize myself and the world with it, right? And thus it becomes an elementary function. Well, actually, it doesn't become an elementary function, it becomes a special function. Elementary function, the set of elementary functions is closed, I'm afraid. That's so that's not, if there's an important equation to which you anticipate returning, it's worth just, this is kind of a fancy way of saying tabulate the damn solution, right? So that's what humanity does, right? When we don't understand something, we make a table, or these days an Excel spreadsheet, right? And then that creates, if not understanding, at least a kind of familiarity that is then key to contempt and successful operation of the modern society. So now, so here are some non-general strategies of finding solutions to equations found in undergraduate problem sets. So, so the first solution is, the first idea is this: try y equals to e to the lambda x. Stick this into the equation and see if you can find the lambda for which it works. I'll show you an example of that in a moment, but let me give you a few more. If that doesn't work, try y equals to x to the n. N doesn't have to be an integer. Stick it into the equation and see if you can find an n for which this works. Right? There will be an example of that too shortly, but suppose it doesn't, right? So suppose this is not a solution, but let's see how I want to do this. Sorry, I forgot to say something. So the way, let me rephrase something. So you could check whether this is a solution, or you can do something slightly more general. You can stick this into your equation, and if your equation is such that the coefficients of these a and b coefficients, and possibly also a coefficient of y double prime, are polynomials, right? Then, so they're all combinations of powers of x, right? Then what you can do is you can say, okay, let's find n such that if I stick this into the equation, the coefficient in front of the highest power of n is 0. Okay? So put this into equation and set coefficient of highest power of x to 0. That gives you some value of n, right? Then you get the value of n, then you check, is x to that power of n a solution? If it is, then great, right? If it isn't, so suppose it isn't, but n that you have found is an integer, a positive integer. Then try this. Try the following function. Y equals to x to the n plus some coefficient a x n minus 1 plus etc. plus a n minus 1 x plus a n. So take a polynomial, in other words, of order n. Stick this into equation. So put this into equation and calculate the coefficients ai for which this is a solution. Okay? This usually works. I omitted to say, which I should have done, that the first method, y equals to lambda x, is also only worth using if the coefficients of the equation are polynomials. Okay? So let's do an example of that. So you have several such examples in your problem set. Let me do another one, which is not in your problem set. So let's consider this equation. Now, I don't know how good you are at spotting solutions, so I don't know whether you can tell me right away that something obvious is a solution of this equation. So, but here's a systematic way of figuring out, right? So let's try y equals to x to the n. And what I'm going to do is I'm going to figure out what is the highest power of n. Sorry, what is the highest power of x in this equation, and set the coefficient in front of it to 0. So the highest power of x obviously comes from this term times y double prime. So it's 2x squared times, when I take double prime of this, this becomes n times n minus 1 times x to the n minus 2, right? So this term will give you a lower power of x, so it doesn't matter at this point. Here, this term will give you the highest power, so it's minus x times n x to the minus n. And here, the highest power will be obviously x to the n. And I want this to be 0. So x to the n is the highest power everywhere, so all the x's cancel. And I find, so the n can be scaled out, right? And so I find 2n minus 1 times n minus 1 is equal to 0 for this to happen, right? So there are two solutions. Let me first try this one. N equals to 1/2. Okay? So well, that means that we are asking whether perhaps square root of x is a solution of the equation. Well, if you substitute this into the equation, you will find that yes, it is indeed a solution, just by substitution. So the answer is yes, a solution by substitution. You can check. So then the prescription of the buy one, get one free deal is to look for general solution in the form y equals to square root of x times psi. Well, then y prime is psi square root of x plus psi over 2 over square root of x. Y double prime is psi double prime square root of x plus psi prime over square root of x minus psi over 4x to the 3/2. Right? I just differentiated that. So now let's substitute both of those things into the equation. So 2x, x plus 2 times psi double prime square root of x plus psi prime square root of x minus psi 4x to the 3/2 plus 2 times 2 minus x times that, which is psi square root of x plus psi over 2 square root of x. And the last term is y, which is plus psi square root of x, and all of this has to be equal to 0. Let's see. What have I done? This should be a prime. And this should be a prime. Well, so because square root of x is a solution, or just by checking directly, this term, and this term cancel. Again, you can check this if you like. So these all cancel. And then I have to collect everything else. And to collect everything else, it's convenient to multiply the whole thing by square root of x. If I do this, then this square root of x will disappear, this one will become x, and this one will become x. So after these manipulations, let me save time by telling you what will happen. So x plus 2 this will happen. And this is just a linear equation that we can solve, right? So how do we solve this equation? Well, by separation of variables, right? So psi, so you rewrite it as psi double prime minus x plus 6 over 2x, x plus 2, psi double prime. And so this is d psi double prime by over psi double prime is equal to minus x plus 6, 2x, x plus 2 dx. And then you integrate both sides. So to integrate this, you say minus dx over 2x plus 2. And here you have minus 6 dx, actually minus 3 dx x plus 2. You split these two into two terms. So do the integrals, and if you get through the algebra on this, what you'll find is that psi. So you will find that this is log psi prime plus a constant, of course, right? This you integrate, you get a bunch of logs. Once you've done everything, you get psi prime equals to c1 1 over 2 square root of x plus 1 over x to the 3/2. Then you integrate that, and that gives you c2 plus c1 square root of x minus 2 over square root of x. Then you remember that y was psi times square root of x, and that gives you c2 square root of x plus c1 x minus 2. And that's your general solution. Okay? So, well, so that's a quick example of how to do these things. Now, let me notice that actually I could have done it slightly differently. I could have said, no, the solution that I like is not n equals to 1/2, but n equals to 1, right? So I could try n equals to 1. If I tried n equals to 1, that means I'm looking for y equals to x. Now, if you substitute y equals to x into that equation, it turns out it's not a solution. Okay? So according to the prescription I've given you, you should be looking for a solution in this form. X, let me call it alpha since I used the A before. X plus alpha. If you then take this and substitute into the solution, what do you think is going to be the value of alpha? -2, and indeed you can check that that's really true. So exercise, now take this solution x minus 2. Pretend that you don't know the other solution is square root of x. Look for it via variation of constants, right? So try y equals to psi of x times x minus 2. And solve the problem again and see if you can recover square root of x as the second solution. Okay? Another exercise that you can set yourselves is to put in some function here, f of x, and see if you can solve it with that function. Simplest example, f of x is equal to 1. Oh, actually, sorry, not here. This was a severe case of blackboard blindness. I'm sorry. It's right there. Right? Put the function f of x here. Make it equal to 1. Now, generally speaking, what is the solution to an equation with to the inhomogeneous equation? Well, it has to be the solution of the homogeneous equation plus a particular integral of this equation. Now, the particular integral for, if you put a 1 here, you can guess. What is it? 1, exactly, right? So it's y equals to 1 works. So the solution is actually just this plus 1. But you can check whether, if you pretend that you can't guess it, you can, by the general method that I have described, by varying constants, figure out what that solution is. And the advantage of such an exercise is that you know the answer, so you know whether you are right or not. Okay. Let me now do another example, which actually qualifies as a whole section of this course. So, but it is essentially an extended example. So let's do second order linear ordinary differential equations with constant coefficients. And first I will consider the homogeneous equation. So we're considering the following example, and I will call my variable t again because it will be useful for me to think of it as time for physicsy purposes. So y double dot plus ay dot plus by equals to 0. A and b are constants now. So in previous calculations that I have shown you, a and b were functions of x. Now they're constants. So a and b are constants. So to this equation, to solve this equation, let me use one of the other strategy that I suggested to you, which was try an exponential. Okay, let me show you how that works. So let's try y of t equals to e to the lambda t. So let's substitute this into this equation. What am I going to get? I'm going to get lambda squared e to the lambda t plus a lambda e to the lambda t plus b e to the lambda t equals to 0. E to the lambda t cancels nicely, and I get lambda squared plus a lambda plus b is equal to 0, which is a quadratic equation with two roots. Minus a plus minus a squared minus 4b divided by 2. Right? Now, so if a squared is not equal to 4b, this is great because we have two roots which are not equal to each other. So not only have we found a solution that satisfies this equation, we found two such solutions. And because lambda 1 and lambda 2 are different, the two solutions we have found are linearly independent. Okay? So e to the lambda t and e to the lambda 2t are linearly independent solutions. Therefore, the general solution is C1 e to the lambda t plus C2 e to the lambda 2t. Problem solved. If we want to dwell a little bit on what is it that this says to us about the solution to the problem, well, there are two obviously interesting cases. One is if a squared is larger than 4b. This is a b, not a 6. So if a is larger than 4b, then both lambdas are real, right? And so your y is equal to e to the minus at over 2 c1 et square root of a squared over 4 minus b plus c2 e to the minus t square root of a squared over 4 minus b. Right. So what this describes, and this is guaranteed to be positive, so this and these things are real. So what this describes is a linear superposition of two exponentials that are either growing or decaying, depending on the sign of a and this, yes, depending on the sign of a. Okay? So one of them will necessarily be growing faster than another or decaying slower than another, which means that if I wait long enough, that's the one I will be left with. Okay, so after a long enough wait, you're only left with one of these solutions, the other being exponentially small. Okay? So the other possibility is a squared being less than 4b. That's the situation in which under the square root we have negative numbers. And so the two solutions are complex. And so y then becomes e to the minus at over 2 c1 e to the I omega t plus c2 e to the minus I omega t, where omega is square root of b minus a squared over 4. So now, well, typically when I solve differential equations, I want real solutions rather than complex ones because they describe physical quantities. And so I can rewrite this as e to the minus at over 2, some constant times cosine omega t plus another constant times sine omega t. So I have now hidden the complexity inside the constants, and of course the constants can be anything, including real, which means that it is possible to find a real solution in this form, or by standard trigonometric identities, I can write this as e to the minus at over 2 times alpha times cosine of omega t minus phi. And I'll leave it to you to figure out what alpha and phi are in terms of a and b. Right? That's a high school problem. So, so this solution then is something that decays or grows at the rate a. Well, if a is negative, then it grows. If a is positive, then it decays. There is some amplitude, which is completely free because the equation is linear, right? So the amplitude can be anything. And then there is a frequency that's determined by the coefficients of the equation, and there's a phase shift, phi. Okay? So now, if a, and in this context I will call it gamma, and if it's larger than 0, and b is also larger than 0, and I will call it omega naught squared for these purposes, then what we have is something known as a damped oscillator, right? So then I can take my equation, where is it? Over there, and I can rewrite it as y double dot equals, plus gamma y dot plus omega naught squared y equals to 0. So this, actually, we've encountered this equation briefly last week, right? This is a damped oscillator. So this bit, without the gamma, right, that's just a simple harmonic oscillator with frequency omega naught, right? And if I add gamma y dot, well, this is a force proportional to velocity, right? So this is friction, right? So friction, and this here is the restoring force. So this can be gravity for a pendulum, or hook tension for a spring, and this kind of thing. And this is, as I said, just friction. So that's this standard physical interpretation of this equation. And so it's an oscillator, so it will oscillate at the frequency which is omega naught squared minus gamma squared over 4, right? That's according to, because I renamed B and A, this is now what it is. So you see that this frequency is somewhat lower than the own frequency of the equation, right? So actually it's almost the same if the damping rate is much smaller than the rate at which the oscillator oscillates, which it should be if we want it to be an oscillator. Okay? So now some nomenclature, if omega naught is larger than gamma over 2, which means the frequency is real, this is called an underdamped oscillator. If omega naught is less than that, then it's called overdamped. And then it's actually not an oscillator. It's, we're back to the case where a squared is larger than 4b, and this is just something that decays. Well, what are we going to do, though, if this is not satisfied, right? If the two frequencies are not the same. So what if lambda 1, if the two lambdas are the same. If lambda 1 is equal to lambda 2, that means that, so this will happen if a squared is equal to 4b, so lambda 1 is equal to lambda 2 equal to lambda and equal to minus a over 2. Well, then we don't have two solutions available to us, right? But we do have one, right? We do have one. So this here is still a solution. Let me actually call it minus at over 2, like that, right? So this is still a solution. And we can try to find the second one. How? Again, by weaponizing the constant in front, right? So you put the psi in front and see what happens. Well, let's see what happens. Well, okay. So this is now y, right? So that's going to be the general form of the solution. And this here was y1 of x. Well, again, y dot is equal to psi dot e to the minus at over 2 minus a over 2 e to the minus at over 2 times psi. Y double dot is equal to psi double dot minus a e to the minus a psi plus psi times e to the minus at over 2. Did I do this right? No, I have to say this is, sorry, a squared over 4, like that. Okay. I'm not actually as bad as this at algebra, but when one does this in front of a board, when you have your algebra 50 centimeters from your nose, you experience what's known as blackboard blindness. Right? You have to, that's why you guys are much better at it, because you can see it from a distance, and so you have a wider opening angle on this on this calculation. Anyway, so we plug that into there, and what do we get? We get psi double dot minus a psi dot plus a squared over 4 psi. That's the first term, plus a psi dot. That's the second term, plus b psi equals to 0. Okay, and this cancels, and this cancels as well, because remember we're considering the case where b is equal to, where a squared plus 4b is 0. Right, so this is also 0. So we get a beautifully simple equation. Right, psi double dot is 0, which means psi is C1t plus C2, which means our general solution of our equation is C1t plus C2 e to the minus at over 2. So, and again, we have two linearly independent solutions. One of them is e to the minus at over 2, which is e to the lambda t, right? So that's the one we found. And the next one, the one that we got for free, is the same multiplied by t. Now, when you're solving such equations, you don't have to go through this procedure every time. All you have to remember is, to get the second solution, multiply by t, right? But go through it once to know where it comes from. Right. I think we should make a break for 5 minutes and then continue.